Okay, hi everybody. We are talking here differential equations, section 2.2, separation of variables. Thanks for your patience on this video. We made it safely to London, and right now it's 9:18 p.m. on Sunday night in London. Okay, so separation of variables is also called separability. It's also called separability. That's not what I wanted to do. Also called, here we go, separability. It'll be our first solution technique we learned, and we'll use it to solve first order separable differential equations that are both linear and nonlinear. So let's look at solving a non-autonomous first order differential equation like we've used before. Okay, so let's take the differential equation dy dx equals 1 plus e to the 2x again. It's non-autonomous because the right-hand side has an x present, an independent variable. The right-hand side is not explicit by y, the dependent variable. So let's take dy and let's keep it on the left, and then 1 plus e to the 2x and on the right, and then let's move that dx to the right just like you would if you were dealing with a u substitution and taking the derivative and moving the dx to the left. And we have the integral of 1 dy on the left, integral of 1 plus e to the 2x on the right, and on the left then that would become a y plus some constant, maybe d, is equal to x plus e to the 2x over 2 plus some constant, maybe g. And then when you combine the constants and move the d from the left to the right, we get y is equal to x plus e to the 2x over 2 plus, let's rename the constant as c, where c is the g minus d, where c is equal to the g minus d. Now, you don't need to keep track of constants like this, the d and the g. Moving forward, we'll just put the c on the right, but at least this way you can see how we would have a constant on the left, we would have a constant on the right. They could potentially be the same or different, but then when we combine them over on the right, they become one constant. Okay, what does it mean for a first order differential equation to be separable? Again, we're talking about the solution technique, separation of variables, and to be able to use separability on a linear or nonlinear first order differential equation, that equation has to be separable. So a first order linear or nonlinear differential equation is separable when the right-hand side, the function we've named f by independent x and dependent y, is a product of functions. We have a product here, product of two expressions, an x expression or an independent variable expression. And so I'll change it to an independent expression and a dependent expression. So now let's look at some examples and we can decide if they are separable or non-separable equations. Again, they're all first order. Check. They're all raised, or the highest derivative is 1. And then let's look at when the derivative is on the left and everything else is on the right. Let's check to see if the right-hand side is a product of an independent expression and a dependent expression. The first one, here's your independent expression. Here's the dependent expression, and it's a product. So this is separable, that first equation. Let's see, number 2. Right now it's not a product, but maybe we could factor, if you factor out, let's see, a t, then we'd be left with y plus 1. And now, yes, we have an independent t, dependent y plus 1, and it's a product. So this equation is separable. The third one, it's only in terms of t, but we could treat it as an independent expression times a constant, which would be in terms of the dependent variable. So yes, and it's a product. So yes, separable. But this last one, we have independent x, dependent z, but it's a plus, not a product. So not separable. Even if we tried to factor out an x or factor out a z, we'd still not end up with two expressions. One in terms of x, one in terms of z. Next up, we will look at solving differential equations with separability. Okay, here we are with number 1. I think we're going to look at 1, 2, 3, and a fourth one. Okay, so let's go to number 1. And we're solving a differential equation. We're going to use separability because it's first order. It's a linear differential equation, could be linear or nonlinear, and use separability, but specifically because it is a separable differential equation. We're going to look for an explicit solution, meaning we're going to look for a solution that's y is equal to a right-hand side that's explicit by the independent variable. So let's collect all the, we're going to treat dy dx as a fraction, even though it's not really. And we're going to move all the y pieces to the left side of the equation and all the x pieces to the right. So here's our equal sign. We have a dy on the left. If we divided both sides by y, then we'd get 1 over y on the right, or sorry, on the left. And then we currently have an x squared. We'd multiply the dx over. Then the next step would be to integrate, and we'd end up with natural log absolute value y is x cubed over 3 plus our constant, and that constant again is the collected constant from both sides of the equation. Now we want to remove the, let's see, this right now, this is our implicit solution. Implicit solution because it's not a y equals something or an x equals something. It's a solution to the equation, but it has x's and y mixed around with it. So now we want to solve explicitly for y in terms of x. We want to raise both sides as powers to the base of e. So the left side, we have natural log y, or sorry, absolute value of y. On the left, this is an e raised to all of this stuff. And just for a quick little refresher, if you had a to the x plus y, this is the same as a to the x times a to the y. So we end up with an e to the x cubed over 3 times an e to the c. Then we need to remove the absolute value bars. And when we do, let's think about that. So let's say we had, let's use blue. The absolute value of something is 5. What are our options for the question mark? What could it be? What could it have been? It could have been a plus 5. It also could have been a minus 5. So when we, either one, when you take the absolute value, that inner part could have been plus or minus to still give you the plus 5. So when we remove the bars on the absolute value, the y could have been plus or minus y is, let's put the e to the c in front, e to the x cubed over 3. Then I'm going to move the plus and minus to the right-hand side of the equation, plus or minus e to the c. e to the x cubed over 3. And this is your solution. You can leave it this way, but a lot of times you're going to see this plus or minus coefficient renamed as something like a. So let's use a e to the x cubed over 3. There's our explicit solution. Yes, and here at the end, this is our explicit solution by x. It's y equals stuff with x. Okay, next one. Y prime equals 6 plus sine x all over y plus cosine y. Find an implicit solution. So once we find a solution, we don't need to solve for y. We don't need to solve for x. All right, so let's treat that dy or that y prime. It might be helpful to treat it as a dy dx equals, and then the other stuff, 6 plus sine of x all over y plus cosine of y, and then we're going to move all the y things to the one side, x things to the other side. Usually I put all the y stuff on the left. So if here's our equal sign, and we multiplied both sides by this denominator here, then we'd end up with y plus cosine y dy on the left. On the right, we'd have 6 plus sine of x, and then we're moving the dx over, and then we need to integrate. And after integrating, that's a y squared over 2 plus sine y, that was your daily problem from the other day, equals 6x minus cosine x, and then plus our constant. There's our implicit solution. Here is our third one. We have one more after this. This time we're going to find an explicit solution to the initial value problem. Here's your differential equation. Here's the initial condition. So we're going to solve the differential equation, and then to recover the constant, we're going to plug in the initial condition to change the constant from a constant to an actual value. Now, this is a first order differential equation. It's non-linear because take the y prime, for example. That dependent piece has a coefficient y that is not a constant, and it is not depending just on x. It's not an expression of x. So first order nonlinear differential equation. And let's, again, I'm going to rewrite the left side as dy dx. I'm going to put the y, here's y, and then 1 minus 2t. Okay, so the independent is t, which means I need to go back and change this dy dx to a dy dt. Okay, right side, 1 minus 2t with a dt. The left side, I'm going to put the y in front and the dy next, and then we're going to integrate both sides. We'd get y squared over 2 is equal to t minus t squared plus a constant. There's my implicit solution. Now we want to recover that constant. So let's do that. Recover, here I'll write it over here. Recover the constant, the c, the parameter, with or by using the initial condition. And that condition was 1, negative 2. So when t is 1, y is negative 2. Let's plug that n. Y is -2, so -2 squared is equal to 1 minus 1 squared plus c. So we put for this y, we put in, for this y, we put in a -2, and for these t's, we put in 1s. So on the left side, that's going to be 4 divided by 2, 0 plus c. 2 is equal to a c. So now let's update our solution. Update the general solution, which we had y squared over 2 equals, and t minus t squared plus c. But c is no longer a c. C is a 2. And this is an implicit solution. Did it say explicit? Yeah, we want an explicit solution. So let's go back and notice if we solve for, let's find an explicit solution. If we solve here for y to get an explicit solution, we would move this 2 to the right-hand side. We'd multiply the whole right-hand side by 2. We'd get y squared is 2t minus t squared plus 4. And then you'd take the root of both sides to get rid of the y squared. So y would be plus or minus the root of 2t minus t squared plus 4. But then you have to pay attention here. So this is telling you the solution y outputs to a plus value or a minus value, and we're going to need to pick one in this case because of the initial condition. So notice the initial condition has the initial condition outputs a negative value. That means we need to keep the negative value in our solution, and our explicit solution will be negative root 2t minus t squared plus 4, and it's negative again to match the negative output in our initial condition. If we plugged in a 1 into our solution down here, it would, let's see, if we plugged in a 1, that's 2 minus 1, that's 1 plus 4, and when we get a root 2, we want it to be negative, so we need the negative sign out front. Okay, last one, and this is our exponential growth problem. We have p prime equals kp, and here again, first order, let's write it as dp dt. K is a constant. This is value dependent variable p, and let's use separability. So we'd move the p to the left side, 1 over p dp. We could keep the k on the right, move the dt over, we'll integrate. The left side becomes natural log absolute value p. The right side becomes kt plus a constant. And then let's raise, exponentiate. Let's raise both sides to a power with a base e. That means the left side is absolute value p. Right side is that e to the c, e to the kt, like we've done before earlier. And let's see, that was this problem here in the beginning where we had e to some things and we wrote e to the c. We had e to some things here, and then we wrote e to the c times e to the x cubed over 3. Doing a similar thing right here and right here. So let's drop the absolute value bars. Let's do plus or minus e to the c, e to the kt, and then let's rename. Let's make p equal to a e to the kt. There's our solution. And it's explicit because we have p is equal to just something in terms of t. And here we have, again, our exponential growth equation, which we have discussed solutions about before, but this is the first time we've actually solved that equation. And just to convince yourself, if we calculated the left-hand side, dp dt, that's equal to the derivative by t of a e to the kt, and this gives us k a e to the kt. If we calculate the right-hand side of our differential equation, that kp, then we end up with k times p, that's k times our solution down here, a e to the kt, and look, we get k a e to the kt, and those left and right hand sides match, so it is a solution. Okay, thanks for tuning in. Please reach out with any questions, and I will post the other video sent for integrating factor.